The Garage by Credo is a podcast about invention and innovation, exploring the minds of innovators throughout history and shining a light on the products that are transforming the world today. Through conversations with entrepreneurs, inventors, garage tinkerers, and other passionate creators, this show will bring listeners inside the metaphorical and oftentimes literal garages of the world, exploring the potential for world-changing ideas that often originate from the most unlikely of places. In this episode, we are joined by Mike Grace, founder and CEO at Longshot Space. Longshot is building a hypersonic launch system in Oakland, California. Their approach is poised to make access to space dramatically less expensive, which according to their mission, will help expand human activity in space by orders of magnitude. Today, we'll take a short journey back in time to explore the origins of the modern rocket. In so doing, we'll attempt to answer the question, why do we go to space with rockets? And what does the future look like if we were to uncover a cheaper and less lethal alternative? Finally, we'll learn about the space gun, a new idea that's actually pretty old, and a system that ironically is a really bad weapon, but might be a really efficient alternative for launching things into space. Let's jump into it. I guess we'll start it out, maybe just kind of introducing yourself and just describe what you're building.
My name's Mike Grace, and I am the CEO of Longshot. Longshot is building a hypersonic accelerator. In the near term, we're lobbing stuff at the sort of mid to high hypersonic speeds into the atmosphere for people who want to develop heat shields and guidance systems and all kinds of fancy whiz-bang, zoomy-boomies. And in the long term, what we want to do is build this system up for basically investing a ton of kinetic energy into a payload and then putting that payload into space for very, very, very low cost.
That's awesome. Yeah. And I definitely want to talk about your project and the economics of space. I had a chance to go down there and do some filming and see the prototype, which is super badass. And so definitely want to hear more about that. I think it'd be cool to start with what got you into this in the first place. And then maybe we can go back and kind of dive into some of the history of rockets as a weapon system and why we even use them today. Because I think that's super interesting, kind of how you frame what you're building against that. So I guess we'll start with how did you get into building a space gun?
I've always been really interested in space, and I've always, I think that it's super important for the future. I think that humanity kind of scratches out of existence on sort of the raw materials we have on the surface of the earth. And if we want to have a future of basically unlimited abundance, we've got to get access to the materials that are available to us in the solar system. The solar system is made of enough iron and copper and carbon and lithium to support a human civilization of trillions of human beings. So if we can get access to that, it basically means an end to material constraints.
Humans have likely been fascinated by the cosmos since the earliest days of our evolution, but it wasn't until the beginning of the 20th century that we began to take the first real steps towards exploring it. Our modern concept of space travel goes at least as far back as 1865, when Jules Verne published From the Earth to the Moon, a story of the Baltimore Gun Club, a post-Civil War society for weapons enthusiasts, whose goal was to build an enormous gun and fire a projectile with 3 people to the moon. Included in the text were some rough yet remarkably accurate figures of how humans could actually reach the moon. This story would ignite the imaginations of many, like Konstantin Tsiolkovsky, one of the founding fathers of modern rocketry, and the man who formalized the rocket equation. His work serves as the basis for much of the spacecraft engineering being done today. With the turn of the century and 2 major wars, the world witnessed a major shift in scientific destruction. This would eventually involve Tsiolkovsky's rocket equation and some other frightening weapon systems, some which were more effective than others.
This is an observation that I would make that apply both to World War II and World War I, is that when an industrial superpower is on the losing side of a war, they really start swinging for the fences, technologically speaking. And the Germans did this a lot in both wars. They built crazy stuff, gigantic Zeppelins for high-altitude bombing, and they also built superguns. So the superguns that the Germans built in World War I, the kind of creme de la creme with this was we know it as the Paris gun. This was basically a system that was designed to lob projectiles, I believe, over 120 kilometers distant. So it could start well behind German lines and lob projectiles and actually put them down into Paris from a safe distance. And the engineering of that gun system and the testing of that gun system is totally crazy. But if they had just taken that gun and they had done this, they would have beat the Russians into space by, a good 40, 50 years. So a couple things to note about the Paris gun, and this is also true of a lot of German super weapons, both in World War I and World War II, is that it was a terrible weapon system.
The Paris gun was a giant siege gun used during World War I to bombard Paris. It was the largest piece of artillery used during the war and was so powerful that Parisians believed that they were being bombed by a Zeppelin. The shots seemed to come out of nowhere. Although a terrifying weapon in theory, the Paris gun was ultimately a psychological one, designed to attack the morale of the people of Paris, but not necessarily effective in slowing down the enemy. This wouldn't be the last time the Germans deployed a massive gun during wartime, but as the First World War wound down, there was an emerging interest in more advanced systems based on the principles of space travel. Around this time, a handful of pioneers like the American Robert Goddard were doing foundational work on rocket systems. Goddard was an engineer, professor, and inventor, and is credited with building the world's first liquid-fueled rocket. His 34 launches and 214 patented inventions, such as the multi-stage rocket and liquid-fueled rocket, paved the way for a new era of spaceflight. Though his work during the interwar period would eventually cement him as one of the founders of modern rocketry, he was mostly unsupported by the public and ridiculed by his peers. Facing different circumstances in post-war Europe, his counterparts in Germany found a leg up in the race to develop the first vehicle propelled by rocket engines. When World War II rolled around, they were in the lead.
The Germans we had Robert Goddard in the United States. We had some of our own rocket experts. But at the time that Robert Goddard was building these little tiny gasoline-powered liquid-fueled rockets in sort of the interwar period, the Germans were way ahead. They were building very large systems which would transfer relatively easily into the rocket motors and the rocket systems of World War II. The reason the Germans were so far ahead in World War II in rocket development was because at the conclusion of World War I, in the Treaty of Versailles, you can go through the Treaty of Versailles, there's a very particular provision in there which explicitly says, look guys, you don't get any more gigantic gun facilities, and French and British inspectors are going to be put into your industrial facilities to make sure you are not developing the capability for building these very large guns again. No more Zeppelins, no more mustard gas, no more shells, none of this. That was all basically part of the kind of de-weaponization, demilitarization of Germany that was imposed on them post-war. So the Germans were really desperate to try and develop a technology that would give them very, very long-range weapons capabilities. And so in the interwar period, the German government heavily subsidized the development of rocket motors and of rocket technology. And so the Germans were 10, 15 years ahead of everybody else in the world come World War II. Now, let me digress a little bit and talk about the V3, which is actually a weapon system that not many people have heard about. And the reason for that is that similar to the Paris gun, it kind of sucked as a weapon system. It wasn't actually very good for a weapon.
What were the big iterations from the Paris gun to V3? Why did they think that this time around it might be a better weapon of choice?
Well, again, I think that the idea was, I still think, a little bit silly, and that fundamentally what Hitler wanted to do with these was build an array of them buried in northern France, pointed at London, to threaten to level the city. Hitler was really fixed on this idea that if the British would just stop fighting, that he'd just win. And he may have been correct early in the war. I think later in the war, it was no, this has gone too far. This is not going to stop. But the idea of threatening to literally level London to convince the British to capitulate was a really strong idea he had. So basically bury a bunch of these systems in northern France and then just use them to put shell after shell after shell down onto London. Actually kind of a similar idea to what the Kaiser was trying to do in World War I. And I actually think in both cases, not that great of an idea. It turns out that having a dictator hopped up on methamphetamine may not lead to the best strategic decision making.
In 1918, the French army responded to the German Paris gun by designing a long-range, multi-chamber gun, although the plans didn't reach the prototype stage and were later archived. France collapsed in June 1940, and at the beginning of World War II, the German troops acquired the plans for this long-range gun, which led to the development of the V3. This weapon used the multi-charge principle to fire multiple secondary propellant charges to add velocity to the projectile. The Germans planned to use the gun to bombard London, but they were rendered unusable by Allied bombing raids before completion. History has a funny way of repeating itself. The V2 became the first artificial object to travel into space on the 20th of June, 1944. The rockets traveled at supersonic speeds and impacted without audible warning. They proved unstoppable, with no effective defense system existing.
The V2 was scary, but it had an explosive warhead on it. And that explosive warhead was really comparable to what a bomber would drop. The difference between a bomber and the V2 is that there's no stopping the V2. They just move too quickly. This is a very supersonic thing. It's basically going to the edge of space and then coming back down. So you have this unstoppable delivery system that the Germans develop and display in World War II. Literally, again, thousands of them launched. At the same time, the Americans have their own superweapon project, and they build the atomic bomb. And the pairing of those two things is really obvious to all the belligerents in the world. If you have a delivery system that effectively cannot be stopped, and you have a weapon that can level cities, a relatively compact weapon that can be put on top of one of these things, that was obviously going to be the weapon system that was going to define the post-war world. So both the Americans and the Soviets saw all these things. The Americans displayed the atomic bomb in Japan. The Germans displayed the V2 in Europe. And it was very obvious where the weapons development technology was going to go, which, the Americans and the Russians really wouldn't be able to replicate for another 4 or 5 years after the war. And that was mostly because we both stole a bunch of V2s and a bunch of the scientists who had made the V2s. Both the American and the Soviet space programs were effectively built by this long legacy of we both basically stole a lot of German technology.
To summarize it here, so you have the Paris gun in World War I, you have the V3 in World War II, you also have the development of V2, which is essentially the first modern rocket system? Is that a fair way to
I would say it's the rocket system from which all modern rocket systems are descended. It is every modern rocket, liquid-fueled rocket, starts with the V2.
After the Nazi defeat, German engineers were relocated to the United States, United Kingdom, and the USSR, where they further developed the V2 rocket for military and civilian purposes. The V2 rocket also laid the foundation for the liquid fuel missiles and space launchers used later. The seeds for the first race to space were sown. The competition of the 50s and 60s brought major advances in spaceflight, from artificial satellites and robotic probes to the Moon, Venus, and Mars. It would eventually lead to human spaceflight in low Earth orbit and see humans land on the Moon for the first time in 1969.
The ability to go to the Moon, the ability to put a man in space and bring him back down, all of these things that building space stations, etc., is really a way of sort of displaying technical competency for weapon systems that could potentially destroy the world without having to go and test atomic bombs. Because the rockets, in many ways, are actually the much harder part of a atomic bomb stacked on top of a rocket. Atomic bombs are actually relatively straightforward. And once you've tested a couple of those, you have effectively displayed the fact that you can get them to work. But making sure that the other guy knows that you can build these rockets and that they fly and that you can put large stuff into space is really critical if you want to maintain a credible threat. And I think that the whole of the space race, the underlying justification for that, is really that competition. And I also want to say, great things came out of it. I'm a huge fan of the fact that humanity has gone to space, but it was certainly not the underlying, the people who were signing the checks, right, from Congress, etc. They were really concerned about making sure that the Russians knew that we were committed to not falling behind them technologically. And that was totally the Russian justification, the Soviet justification for the same.
As a final act of the original space race, the period of competition would eventually give way to cooperation. The end of the Cold War and collapse of the Soviet Union allowed the US and Russia to collaborate on the Shuttle Mir and International Space Station programs, ushering in a new era of space exploration. This continued on through the Space Shuttle program, but after losing 2 orbiters and 14 astronauts in 2 separate disasters, Challenger in 1986 and Columbia in 2003, there was dwindling interest in space, and the Space Shuttle program came to an end on July 21, 2011, with the landing of the Space Shuttle Atlantis at the Kennedy Space Center. In the 1990s, frustrated by the lack of progress in space exploration, a bold entrepreneur by the name of Peter Diamandis devised a plan. He would create the X Prize to spark new energy and passion in space development. This opened the doors for billionaires like Richard Branson and Paul Allen to get involved, and would see Scaled Composites Spaceship One win the $10 million Ansari X Prize in 2004. This breakthrough voyage launched the suborbital space tourism market and captured the imagination of the world. Around the same time, a small upstart by the name of SpaceX began working on their first rocket, Falcon 1. Launch costs would once again enter the chat, but rockets, originally devised as a weapon system, would remain the primary vehicle for moving things into orbit.
Some of those people who were sort of disappointed in the state of where we were in space, some of those people managed to get really rich. In the dot-com kind of early phases of the dot-com and internet expansion, a whole bunch of nerds made a whole bunch of money. And one of the things nerds tend to be really into, speaking from my own personal experience, is space. And so you've got some John Carmacks, and you've got some Jeff Bezoses, and you've got some Elon Musks. And these guys have grown up thinking, much as I do, that space is really important. And it's also kind of been underinvested and underappreciated, and NASA's not really doing much nowadays, and that's disappointing. Maybe we can do something. So Elon proceeds to build SpaceX. Right now, they seem like a juggernaut. They're absolutely stepping on the neck of the industry. And that's great for them. Awesome. But when they were working on the Falcon 1 and in the early days of the Falcon 9, if 1 or 2 more of those rockets had blown up, they would have gone bankrupt. And the only thing which prevented that company from going bankrupt around 2008, 2009, was the swift intervention of the Air Force and NASA, dumping a bunch of money into the company through the Commercial Crew program. I mean, Elon was just about bankrupt, putting money into Tesla in 2008. He would not have been able to save it. So rockets are hard. I think it's incredible that SpaceX has been successful, and they have completely, and I would say single-handedly, reshaped the industry. The people who are credible to compete with SpaceX, the people who, like, if you're an investor or you're a third party and you're not an expert in the industry, the people who are credible to compete with them are really smart rocket scientists. And really smart rocket scientists look at a company like SpaceX that managed to build a rocket and really change a market with it. And they look at that and they see this company built a really good rocket, and the market really wanted a really good rocket, and I could build an even better rocket. I could build a rocket with like an all fiber or all carbon fiber frame, or I could build a rocket that's 3D printed, or I could build a rocket that has a toroidal aerospike, or I have a rocket that has a different fuel mixture that's more efficient. And the thing that I would criticize about that, and that I think is the mistake, is that it actually enormously underestimates the breadth of things which are completely 100% necessary to be successful. That having a really, really cool, really awesome rocket was actually only really a necessary prerequisite for SpaceX's success. There was also an enormous amount of hard work, an enormous amount of luck, and an enormous amount of really good timing that was stacked on top of that made it successful. And so I would say that there was a big wave of companies that sort of started up in the wake of SpaceX's initial success. I would say around like 2012 to 2015 or so, where they had really brilliant technical founders, some of whom came out of SpaceX. And they said, we could build a better rocket. And it's going to be 5%, 10%, 15% more efficient than that rocket. When in fact, the rocket's a tiny portion of what makes the company work and what makes the company successful. You could have a better rocket, and your most likely outcome will still be failure.
Is it kind of like something where if you want to beat SpaceX, you also have to, you not only have to build a better rocket, but you also have to build a better constellation system in space and sort of doing all the other things that they're doing to try to squeeze profit out of this?
Absolutely. And, if you look at the prospectus for Astra, which is a small launch company that is based here in Northern California, or Rocket Lab, or any of the other sort of more credible small launch companies, every single one of them has some kind of a pitch for how they are going to leverage their launch system to build an in-orbit capability. Because it's become very clear from SpaceX has a valuation somewhere around $150 billion, billion with a B, right? And if their valuation was strictly based on their revenue and expected revenue growth from space launch, right, it would be somewhere around maybe $10 billion. Probably less than that. What people are really looking at is Starlink, which is, of course, as you know, SpaceX's telecommunications constellation that they're in the process of deploying in huge numbers right now. And that is where SpaceX gets the $150 billion valuation from, because they're not competing with United Launch Alliance. They're not competing with people who have rockets. They're competing with AT&T. They're potentially competing in telecommunications, and that is an enormous vertical. A lot of money to be made in telecommunications. And if you're an AT&T or somebody else who makes money off of telecommunications via satellites, and you don't have your own rockets, and your best option is to buy rockets you have to get your access to space from your competitor, that's a very, very bad position to be in. So everybody who's building a launch system right now realizes that the big part of the value of getting stuff into space comes from just having access to space, not necessarily from selling those launches.
Decreasing launch costs are increasing the popularity of small satellites. Compared to constellations of fewer, larger satellites, these constellations of small sats are significantly cheaper to make, faster to produce, and easier to troubleshoot due to advances in 3D printing and material science, coupled with improvements in processing power, data storage, camera technology, solar array efficiency, miniaturization, and propulsion. Countries and companies of all sizes are now taking advantage of these advances already. Small satellites make up about 94% of all spacecraft launches, growing from a total of 53 in 2017 to 1,743 in 2021. New companies are leveraging small sats to build large broadband constellations, including SpaceX, OneWeb, Samsung, and Boeing. These decreasing costs, coupled with more widespread technological adoption, has led to an unprecedented era of accessibility for new players in the space industry, from state actors to private companies. As of 2021, the global space industry was made up of over 10,000 private space technology companies, 5,000 large investors, 130 state organizations, and 20 business sectors. Because of falling launch costs, ongoing technological innovation, and growing commercialization in the space industry, new opportunities in both the downstream and upstream segments of the space economy are emerging. Opportunities like manufacturing new drugs and treatments in microgravity, and space mining of precious metals and rare elements. All of these activities will increasingly rely on the availability of supplies sent from Earth.
If you are going to push human beings out into the solar system, particularly if they're going to be staying there for the long term, which is, I think, an important future we need to head towards, you're going to have to... There's going to be a really long period of time where you have to constantly invest. You have to send habitat, you have to send solar panels, and you have to send tools and food and air and materials. It's going to take a long time for an industrial base to be built in space where it can actually kind of sustain itself. And there might be 100 years where we're just investing constantly. And rockets are expensive. I wouldn't be shocked if in my lifetime we can get the price per kilogram down to maybe $500, $400 a kilogram to put something into space with a rocket. I mean, that's compared to historic norms of $20,000 a kilogram. So that would be huge improvement, but I think that we might actually hit a floor somewhere there. With Longshot, putting stuff into space, things that can take 400, 500 Gs, So that's electronics, that's food, that's pretty much everything you can think of except for live people. I think we could get to like $10 a kilogram because, in reality, all our system consumes is electricity that's purchased off of the grid. We use it to compress air, and then we use that compressed air to drive the projectile forward. So I think that if you're going to have a civilization of human beings living in space, and each of those human beings requires tens, potentially hundreds of tons of stuff, it's not actually the price of sending the human beings, which is going to determine whether or not that's economically possible. It's going to be the price of the things that those people need to support them. So our goal is basically, facilitate human expansion into the solar system by making it cheap to send stuff. So Longshot, our technical approach is kind of like pretty significantly influenced by the architecture of the V3 in that it is a multi-injection system. So the core idea there being the same as what the Germans thought of in the 1930s, which is you lower the maximum energy inside of the system by extending it. And that's why the company is called Longshot. We're talking about a very long accelerator, which constantly adds velocity to a projectile using compressed gas. We're not actually using combustion, which is what the Germans used. The actual mechanism of acceleration for how our system actually pushes projectiles is also different from, it's not really a gun. It's actually we instead of pushing from behind, we actually squeeze the projectile from the sides. And the projectile has a long aerodynamic surface sticking off of the rear of it. So a big part of our technology is injecting gas onto that long aerodynamic surface as the projectile travels, as it's going faster and faster and faster. We have to do it with really high precision, really high timing. That's kind of the core of our technology. But if you can build the system long enough, the maximum pressures and the maximum temperatures drop to a point where you can build the stuff out of really cheap materials. So that's kind of like the fundamental insight that we had, was that it's actually way cheaper to build something that's physically large than to build something that's small, but like super exquisite and made out of incredibly expensive materials. We're never going to be able to launch a person with this system. That the accelerational forces are low compared to a gun because the thing is so long, so you're accelerating constantly, but they're still way too high for a person. This is for putting stuff into space: satellites, food, fuel, all those things. And that's where most of the market is.
In order for Longshot to successfully launch things into space, they need to move objects at very high speeds, hypersonic speeds in fact. In aerodynamics, the hypersonic speed is one that exceeds 5 times the speed of sound, starting at speeds of Mach 5 and above. Coincidentally, hypersonic technologies are a hot button topic across the globe. As competition with Russia and China heats up, both are said to have developed their own hypersonic weapons, which presents a new advantage against traditional US defense systems. As we race to develop our own hypersonic capabilities, the government will look to innovators like Longshot to help speed up the innovation process of testing and development for this technology.
If you're trying to build something new, your options for flight testing these things. So you have like a heat shield for a hypersonic. Hypersonic stuff's, like, generally speaking, they get really, really hot because the faster you go, the heat from friction with the atmosphere goes up with the cube of velocity. Not the square of velocity, the cube. So the exponent is a 3. So if you're going really fast, the heat loads can be incredible. So you're trying to develop a heat shield. The only way you can test that heat shield is to put it on top of a pretty powerful rocket that can get up to the relevant speeds. Those rockets can cost between like 5 to 10 million, sometimes 20 million bucks, depending on what you're trying to do. And the range spaces where you can launch them, there's basically only one the United States has access to, and that's the Pacific Range. They basically get launched out to the Pacific Ocean. Those launches, again, 5 to 10 million bucks, and the manifest time to line them up can be 6 months to a year, something along those lines. And that's for a single flight test. That's a problem. So what we realized pretty early on as Longshot is that, if there's this idea for a system that we can build that can launch multi-ton spacecraft and lob those things into the atmosphere at Mach 30, which is orbital velocity, we could potentially build something that is far more humble, far smaller, more contained, that could accelerate projectiles up to Mach 15 or so. Much lighter projectiles up to Mach 15. And those could be like that tool could be a really useful thing if you're Air Force, Navy, Space Force, whomever, trying to work on technical development for advanced hypersonics. So, you know, we tried pitching Longshot as a pure space launch company for a while, but then we realized that we kind of needed this ladder, this rung on the ladder to climb up there. Effectively, for Longshot, from our perspective, the thing that is effectively a scale prototype of our space launch system is a finished product for the Department of Defense, which is great. It just happens to work out that way. The prototype that we're building right now is basically designed to drive a small mass up to Mach 5 and be a basic proof of concept. And that said, it's a small prototype for us because our hardware is big. By small prototype, I mean the thing is about 70 feet long, 6-inch interior diameter. That's the size of the projectile, and it's here in a shed in Oakland. And we test it by accelerating these kind of look like a pair of pucks connected together. And we just accelerate and lob those things into a safe that we filled with concrete. And the maximum speed that we've hit right now is about Mach 2.2, but hopefully by the time this airs, that'll be Mach 5. Mach 5 just being the semi-arbitrary barrier between supersonic and hypersonic. I want to tell people I am a hypersonics company. We do hypersonic stuff.
Thanks for watching the first episode of The Garage. Special thanks to Mike Grace, founder and CEO of Longshot, for sharing more about their hypersonic launch system, guiding us through the history of the modern rocket, and painting a compelling vision of our potential future in space. Also, big thanks to the sources we use for this video, including our good friend Wikipedia, TestTube 101, NASA JPL, the Space Force, SpaceX, Varda, Reckon AL, British Path, Smithsonian, Sven Piper, GPA, Old Movie Collector, Bloomberg Originals, Nguyen Trong Long, and X Prize. If you'd like to learn more about Longshot, visit them at longshotspace.com or look up Mike Grace on LinkedIn, where you can find him musing on the startup journey and the past and future of space. Finally, please check out Credo's recent video of Longshot, which will be linked in the description. If you enjoyed this type of content, please consider subscribing to our channel. We'll be posting a behind-the-scenes tour of Longshot, and we'll be releasing much more content showcasing the incredible innovation happening today. Until next time.